Hello, it's Landon Zagati, a member of Long Island Cares and founder of Food Secure Future, a place for people of all ages and backgrounds to share ideas and learn about the most pressing food security issues. I'm here today with a special guest, Dr. Bruce Rittmann, who has too many accomplishments to list, but to name a few, he received his PhD from Stanford University and is currently a professor of environmental engineering and the director of the Biodesign Center for Environmental Biotechnology at Arizona State University. He is the recipient of numerous awards, including the co-winner of the 2018 Stockholm Water Prize. He published over 720 journal articles, books, and book chapters, and he has 17 patents. Dr. Rittmann has also co-authored the textbook Environmental Biotechnology, Principles and Applications. Hello, Dr. Rittmann, and thank you for joining us today.
Great. My pleasure to be with you, Brandon.
So my first question for you today is, how do microbial technologies play a crucial role in enhancing nutrient availability in soil and ultimately improving crop productivity?
Yes. Okay, so let's go backwards just a little bit. That's a pretty specific question. And so let me just back up a little bit here to provide some additional context for what I'm going to say when I get to the direct question. So first of all, what I do is environmental biotechnology, and the simple definition is we manage microbial communities so that they provide us services. These are services that improve the sustainability of our human society. And those services can include cleaning up pollution, recovering renewable resources, and improving our health. So your question deals most directly with the middle one, which is recovering renewable resources. And so if we look at nutrients and soil, there are a couple of angles on this. So first of all, soil is full of microorganisms, particularly bacteria and fungi, and they are really critical to the good functioning of all soils, whether it's for agriculture or it's just in the ecosystem. And they're constantly recycling nutrients, nitrogen, phosphorus, and carbon in particular, but other ones. They break down complex organic materials, say the plants themselves, the plant roots, or things that the plants exude, and they're releasing all these nutrients back so that the plants can reuse them. So this is a natural process. It's going on all the time. And the health of what we call the soil microbiome is really crucial to the productivity of all of our soils and agriculture, or just in general. So that's going on in the background all the time, and we don't want to be harming our soil ecosystem, microbial ecosystem, because it's providing all these great services. Now, in addition to that, we can do other things that use microbial systems to sort of enhance the process, or even more specifically, enhance the process as the soil ecosystem interacts with human society. And that's really where I come in. I'm not dealing so much particularly with what's going on in the soil, but I'm looking at other factors. So I'll give you one example to kick us off here. And so within the whole agriculture and food system, there's a lot of material, or organic material, that gets lost along the way. Okay, so you grow some plants, you harvest the plants, you don't use all of the plants for food. You may feed some of those plants to animals, and the animals only use maybe about 10%, and the rest comes out the back end of the animal. You do some food processing, either industrial or even just at home, and we don't use everything, and then we don't eat everything. And so there are all these losses along the way of the organic material that was originally formed. All of that material contains nutrients, particularly nitrogen and phosphorus, that, if captured, could be recycled back into the agricultural system, which would create then we call a circular economy of nutrients. And that's what I work on. And so you take these organic, what we now call waste streams, like animal waste, like food processing waste, like unused food, and we use microbial systems to recover the value in it. And there are three types of value in these materials. Number one, there's a lot of energy in it. All that organic material, all that carbon contains a lot of energy, and the microbial systems that I work with can convert that the energy value of in there into either methane or into hydrogen gas that we can recover. And then this is renewable energy that can displace the fossil energy that we use. Two, all that organic material has in it nitrogen and phosphorus. And as we break down the original organic material so that we produce things like methane and hydrogen, those molecules of containing nitrogen and phosphorus are released, and then they become recoverable, so they can be then recycled back into the agricultural sector, and say to create fertilizers or soil amendments. And then, of course, there's water in all of these things, and if you remove all the nutrients and the carbon and everything from the water, you clean up the water, and it then is useful itself for many purposes, such as irrigation or in certain industrial applications. And so we can get the water back, we can get the nutrients back, and we get a lot of renewable energy. It's a great deal. That's what I work on.
Cool. So you're not really wasting anything. You just reuse it.
Yes. We try not to waste anything on that and create truly what we call a circular economy in all of these materials.
It's really cool.
Yeah.
All right. So my next question is, what specific mechanisms do microbial technologies employ to improve soil fertility and nutrient uptake by plants?
Okay, well, I'm going to talk about the second aspect here because that's what I do. So what happens is, so the organic material that comes in, whether it's from the plants themselves or from the animal waste or whatever, is most of it is very complex organic material, large polymers that contain carbon, hydrogen, oxygen, nitrogen, phosphorus, and a few other things. And so what the microorganisms do is they step by step take these very complex molecules and they break them down. And they go, smaller molecules and then still smaller and simpler. And finally, the microorganisms get it to a state where they can produce methane or they can produce hydrogen. And so from the microorganisms' point of view, this is how they get energy to grow. They go from complex to simple to simple to simple. They simplify things, and each step allows them to gather some energy that they use to grow and maintain themselves. Well, so that's their point of view. That's what they want to do. Now, of course, as they keep breaking down the molecules and going from bigger and to smaller and then complex to simple, all the components start to get released. The carbon gets released, the phosphorus gets released, the nitrogen gets released, and all these things get released out into the aqueous environment. And so whether we're capturing energy or we're capturing the nutrients, it's all due to the microorganisms breaking down and simplifying these molecules along the way. And then, of course, we take advantage of that and capture the outputs.
Yeah. So you're just using their normal processes and taking advantage of it.
Correct. This is all natural, normal processes. We aren't doing anything weird.
It's really cool.
Yeah.
So my next question is, what are some examples of successful applications of microbial technologies in real-world farming practices and the resulting impacts on crop yields?
Yeah. Okay. So first of all, this process that I've described here of taking animal wastes and food processing waste and things like that, and getting the microbial systems convert them into energy, primarily in the form of methane, which is the same as natural gas, is fairly commonly used these days. It's not used everywhere. It could be used, but it's pretty widespread. The question then, for me, as a research and development person in this area, is how can we get more people to use this? And that's why we do the research, because we want to make these systems more efficient, more cost effective, so that everybody who has these kind of organic waste streams will say, wow, it's in my best interest to recover all these materials here on it, and not just sort of let them go. So that's what we do in our research, is we try to improve the process so that it will become more technically efficient and cost effective, and everybody will want to use it, and everybody will get these advantages for themselves as well as for the larger society. So that's what we do.
Nice. So next question. How do microbial technologies contribute to sustainable agriculture by reducing the reliance on synthetic fertilizer and minimizing environmental impact?
Yeah, okay. So that's a very well poised question there. So what we want to do here is we want to create this circular economy of the nutrients. And so now most of it just gets lost. And what we have to do when we want nitrogen and phosphorus is we have to create brand new things. So for phosphorus, we mine it. There are big phosphorus mines around the world, and we mine phosphorus and put it in the fertilizers. For nitrogen, most of it is produced by something called the Haber-Bosch process. We take nitrogen N2 from nitrogen gas, N2 from the air, and we reduce it to ammonium and so again, it's created new. Is it the process of producing ammonia nitrogen for fertilizer is very energy expensive, and most of the energy now mainly comes from fossil sources. So we're sort of creating a double problem. We're not recycling the nitrogen plus spending a lot of fossil energy to do it. So there's a lot of problems. So what we want to do is break what we call those linear paths. Linear means from the mine to the field to someplace it shouldn't go, into the waterways or some of this pollution, or from the Haber-Bosch process to the fertilizer to the field to getting lost. So we want to break that linear process, and we want to create a circular process so that when we apply the nitrogen or phosphorus to the fields and we harvest the plants, we then, whether we feed the plants to animals or to us, we want to then capture all the organic material and create a circular thing. So then we can return the nitrogen and the phosphorus back into the fertilizer system, and that will then create the circular economy, greatly reducing our need for mining and the Haber-Bosch process.
So it's not finite. Do you think theoretically it could just go on forever, pretty much?
Well, nothing is 100% efficient. So, it's not that we're going to 100% eliminate any new inputs. That's not a realistic goal, but we can tremendously reduce the inputs of these virgin materials on it and reduce the energy costs and the other environmental implications of it. So our goal isn't 100%, but we want to have it be a major fraction on it. And this, of course, will be a huge change to the agricultural business, particularly the fertilizer business, because people who make fertilizer are now used to bringing in these virgin materials. And we're going to say, well, here's nitrogen, here's phosphorus. It came from another source, but it's the same nitrogen and phosphorus, but they're going to have a different feedstock, and, they're going to have to adapt to this. But I think, they're starting to get the idea.
Yeah. So this sort of leads me into my next and final question, which is, in your opinion, what are the main challenges or barriers to widespread adoption of microbial technologies in agriculture, and how can these challenges be overcome?
Yeah. Okay, well, there are two real challenges. Well, number one challenge is that's not what people are doing now. People will have to change the way they do their business. And, there's always a lot of inertia. People don't like to change. And so just overcoming the inertia is going to be important. And then to overcome the inertia, you're going to have to make to appeal to people in multiple ways. One of which is economics. You're going to have to show them that, in fact, if they do this, this is going to be cost effective, and they're going to actually have a more profitable farm or a more profitable fertilizer business or whatever. And that's where we come in here in our research is to try to make these processes much more efficient. And therefore, they'll be more cost effective, and more people will want to do them, not just for environmental reasons, but also for economic reasons. And then you get the double benefit. You get environmental benefit and economic benefit working together, and then it really works.
Yeah, so that's it for me. Thank you so much.
Okay, very good, Landon. I enjoyed talking with you. And if you have anything, you want to follow up on, feel free to contact me.